So we're looking at differentiation. We're going to be differentiating sine x and cos x. So hit pause, get the heading and lesson objective down. When you're ready, hit play again. So differentiating sine x and cos x. So if y is equal to sine of x, then when we differentiate it, dy over dx is going to be cos of x. It's the result you're going to use quite a bit, and where y is equal to cos of x, differentiate that, we get minus sine of x. So two important results for us. And what we're going to do is going to prove that if y equals sine x, that dy over dx is cos x from first principles. In order to do that, I need two facts. Just draw a line under this then to make a start. Okay, so we need two facts. So we've done some work in radians, and in radians, I'm sure you'll recall this, when x is small, sine of x approximates to x, and cos of x is approximately 1 minus half x squared. If you're unsure, you can have a quick recap through your notes. So when we look at the limits then, this implies that the limit as delta x, very small, tends to 0, of sine of delta x is equal to the limit of sine of delta x is equal to delta x, approximately. So as we approach, as delta x tends to 0, it gives us 1. At the same time, if we look at the limit of cos of delta x minus 1, so in the limit, cos of delta x is going to be 1 minus half delta x squared. So we got 1 minus a half delta x squared. Don't forget the minus 1 there, all divided by delta x. Now the 1 minus 1 cancel out, and we've got delta x cancelling with 1 on top, so that's going to leave us with x tends to 0 of minus a half delta x, which is equal to 0. So those are our two results, and we're going to use them in the proof from first principles. Okay, so we can say first one was the limit as delta x tends to 0 of sine delta x is equal to 1, and limit delta x tends to 0 of cos of delta x minus 1 over delta x is equal to 0. So we're going to need those two facts. So hit pause now, copy these down, and we'll look at first principles. Right then, first principles. Sure, as you recall, just write that down. From first principles, that's not bad underline, dy over dx is equal to the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. I think I'm going to try and use a proper line, makes it easier. Okay, so we're going to use that to differentiate sine of x. So if we go on the left hand side, if we need more space, we can write on the right. So d over dx of sine of x. So using our first principles formula there is equal to the limit delta x tends to 0 of sine x plus delta x minus sine of x over delta x. Okay, so delta x minus tending to 0. Now, sine of x plus delta x, that's the addition formula. So that gives us sine of x cos of delta x plus cos of x sine of delta x minus sine of x all over delta x. Okay, I'm sure you remember the addition formula. Oops, there's the line there. That was very recent. Well, that's equal to, I'm going to do some rearranging then to make it easier for myself. I'm going to collect the sine x's. So I've got sine x cos, sorry, let's rub that out if I can. Yeah, that's better. Cos of delta x minus sine x plus cos of x sine delta x, and that's all over delta x. Okay, so keep it neat. That's equal to, so again I'm going to factorize these two terms. Sine of x is common, so I got sine of x, that leaves cos of delta x minus 1 plus cos of x sine of delta x all over delta x. Now I can split these two terms up. I can put the limit, apply the limit separately to each term. That would be quite handy. So I could say equals to, now the limit as delta x tends to 0 doesn't apply to the sine, so I could take the sine out, sine of x, lim as delta x tends to 0 of cos of delta x minus 1 all over delta x underline plus the limit, I tell you what, we'll take the cos x out. I'll just rub that out. There you go. Rub that out first. Let's put a cos x on the outside. So we can take the cos x out and then apply the limit to sine of delta x. Sine of delta x all over delta x. Okay. Now we can see why we need those results we started off with. So let's see, if I put brackets here and here, oops, and here and here. So our first results in the limit as sine of delta x over delta x equals 1. So this is going to tend to 1. Is equal to 1, and this here is going to be equal to 0. So we've got sine of x times 0 plus cos of x times 1, so that's equal to cos of x, which is what we were looking for. So differential d over dx of sine of x is equal to cos of x from first principles. So what I want you to do now is to hit pause and copy that down. Once you're done, we are going to look at a couple of facts and then move on to the examples. Okay, so let's have a look. If the function of x is equal to sine of x, when we differentiate it, its differential is cos of x. And if f of x is sine of k of x, then when we differentiate that, we get k cos of kx. Okay, so notice the subtle difference then. There's a constant here, and so the constant multiplies cos of kx. Similarly, we've looked at that f of the function of x equals cos of x, so when we differentiate it, we get negative sine x. So in the same way, if the function is equal to cos of k of x, then its differential is going to be minus k sine of k of x. So we've taken that constant that's applied to the variable there, and it multiplies the sine of k of x. So those are 4 results you need to write down and be familiar with. And we're going to have a look at a couple of examples now. Okay, so we've got these two examples. Example A, find dy of dx given that y equals sine of 2x. So y is equal to sine of 2x. So we've got our differential here at the top. So dy over dx is going to be equal to 2 cos of 2x. In this one here, we've got y equals 3 sine 2x. Okay, so essentially we're going to multiply 3 by this result here. So y is equal to 3 sine of 2x dy over dx is equal to the constant 3 times the 2 cos of 2x, which is equal to 6 cos of 2x. Hit pause, write those down, and let's have a look at another example. So for this example, we got y equals 3 cos x plus 2 sine 4x. So when we differentiate it, we get, now when we differentiate in cos, don't forget it becomes minus sine, so it'll be minus 3 sine of x plus, when we differentiate 2, so term by term differentiation, the constant multiplies a 2 on the outside, so it becomes 4 times 2, which is 8 cos of 4x. Hit pause, write the result down, write the example down rather. When you're ready, hit play again. Okay, so let's have a look at this example then. So we've got a curve here with the equation y equals a half of x minus cos 2x. And it says find the stationary points on the curve and the interval from 0 to pi. So we've got y is equal to a half of x minus cos of 2x. So we've got to differentiate that. Y over dx is equal to, if I differentiate a half of x, I get a half. And if I differentiate cos of 2x, that's going to give me, because it's minus, I'm going to change that sign to a plus 2 sine 2x. Now, at the stationary point, what do we know about the gradient? It's going to be equal to 0. So we can say a half plus 2 of sine 2x is equal to 0. That's an x. Rearranging, so 2 sine 2x is equal to minus a half. Sine of 2x is going to be equal to minus a quarter. So I've got to find, I'm trying to find x, so 2x is going to be equal to sine to the minus 1 of minus a quarter. And when I work that out on my calculator in radians, make sure you can get this, minus 0.253. Okay, so make sure you can, don't just copy, plug into your calculator. It's 2x. Now we're trying to find the stationary points between this interval here, but because I've got 2x, I'm going to look at the interval. It's 2 of x, so I'm going to double it. So I'm going to work up to 2 pi. So I'm going to draw my sine curve up to 2 pi. Right, let's do that. So hit pause, copy these down. When you're ready, hit play again. So we're going to sketch our curve up to 2 pi. So there we go. Here's our curve up to 2 pi. We're looking at minus a quarter, and that gave us a result here, negative result of 0.253. By symmetry, when we replicate it here, that's pi plus 0.253, we get 3.394, and here 2 pi minus 0.253, we get 6.030. So 2x is equal to 3.394 and 6.030, which is within our range from here to here. The negative number is not in our range, so to get x we halve them. .030, which gives us 1.7 and 3.02. Okay. Once we got that, so those are our two x coordinates, we can find y. So this implies then, when x is equal to 1.7, y is going to be equal to a half of 1.7 plus cos, oops, close the brackets there, cos of 2 times 1.7, 3.394, which is equal to, plug in your calculator and you should get 1.82. And when x is equal to 3.02, y is going to be equal to a half, just taking it from the formula here, (3.02) plus cos 3.02 times 2, 6.030, which is equal to, should give us 0.539. Okay, whoops, these aren't pluses, are they? These are negatives. Just gonna rub them out. But be careful what you copy down. minus there and a minus there, which is why we got our 0.539 and 1.82. Okay, right, so we've got our coordinates then, and so we've got 1.7 and 1.82, so one set of coordinates, and we've also got 3.02 and 0.539. Good. Hit pause, sketch the graph, copy the notes down. When you're ready, hit play again. You could use Desmos to sketch the curve, to have a look where the stationary points are. And a section of the curve would look like that. It's giving us our stationary points there, or turning points. And the curve, half of x minus cos of 2x, looks like that. Interesting. Right, time for a bit of classwork. Okay, so exercise 9a, 10 questions. Question 1 is very important for you, because now you can use the proof we used from first principles to prove that when we differentiate cos of x, you get minus sine of x. And I think this is quite an important one, so I wouldn't skip any of the questions, work through them. Okay. I'll attach the questions to the assignment.